Back to question number 9. Had a technical difficulty here. Thought I was not recording, but I was. Okay, so what you have here is you want to show S and T are invertible. I think let's go with thinking about the range and the kernel of S composed with T, because S and T, in fact, the composition is also in the operator space of V, or whatever it's called, right? That means that S and T must have surjectivity and injectivity. That means that S is surjective and T is injective, if I remember correctly. And S is surjective when S is inside the operator space, means S is invertible, because it means that it's injective, and surjective and injective means invertible, and the same as T, right? And we're already done, so apparently I just required a fresh change of pace, a fresh change of perspective in terms of thinking. So if S and T are both invertible, I think this side is not too hard, because then what you know is, let's say S inverse S is equal to I, T inverse T is equal to I, and ST inverse is just equal to TS. This reason is because of something like this, right? Oh wait, yeah. And you can also do the other way around for the left inverse. And since this kind of matrix multiplication, which are what linear maps are, they are matrices, linear maps are matrices. Or even if you think about them as compositions of linear maps, is probably even more convenient for this purpose. You see that they are associative, which means you can evaluate them without caring about the order of operations too specifically. So I think this works well. Question 9 works out very well. And let's go back to question 10. Suppose V is finite dimensional and ST are both inside the space of operators, and prove if S composes T is I, then T composes S is also I, right? So first things first, we note that T is injective, because if T is not, and T of V1 equals to T of V2 equals to V, then how do you define S, right? This is not okay. If you set it equal to V2, this is not okay. So T must be injective. And T is injective, that means it's surjective, and T is injective and surjective, that means it's invertible, because we're looking at the operator space, right? So since T is invertible, there should, intuitively there should exist S, which is its inverse. But just because T is invertible and S composed with T is I, that does not mean S is the full inverse, right? It just means it's the left inverse. I don't think in this textbook they mention left and right inverses, but I think that's how you maybe want to think about it. So S is a left inverse of T if S composed with T is I, and S is a right inverse of T if T composed with S is I. So how would you approach this, let's say? So let's say for arbitrary B inside the space, T of B is equal to W, then S of W must equal to, or maybe I don't want to start from this side. Probably want to start from the other side. Let's say for arbitrary v inside the vector space, S of v is equal to some w. Then what is there must exist v1 so that t of v1 is equal to v, because t is injective, which means it's surjective because t is inside the space of operators. And then you know that what's it called? Shoot. Then you know that S composed with T is equal to V2. That must in fact mean V is equal to V2 by definition of the identity, right? And what you can say about that is then, well, T composed with S. This gives you, wait, oh shoot, did I screw up? I think I screwed up. Hold on. I was trying to do this too quickly and I screwed up already. Okay. So S composed with T of V1 is going to be V1. But S of V is also equal to V2. Huh. Okay. But I think what that means is V1 is equal to V2 since S is well defined and not multi-valued. So then what happens is that T of V1 is equal to T of S of V is equal to T of V1, which is equal to V, so that's good, because V1 is equal to V2. So yeah, I guess that was a very tedious way to show this. Perhaps there was a nicer way, I might have missed it. But the thing with things like this is that if you got a left inverse, that means at some point, let's say you got the same set of stuff. You got straight copies of V and S, T, right? So this is T and this is S. S reverse is what you do. Then you put another copy of T here, it's going to invert it once again. That's fine. The problem occurs with infinitely many dimensions. You don't have this with infinite dimensions. It's a bit trickier. So let's try question 11. Because I think for question 10, the other way around is in fact a symmetric argument, right? Obviously, no, keep saying obviously. Lots of these things. If these things were obvious, I could do this in 2 hours, right? I can finish the whole section. But just because it's not, that I struggled 3 or 4 days to get through all the exercises in one stupid section. So none of this is really obvious. I should humble myself and recognize that. In fact, this is a very difficult subject. And I can say this because there are not many math majors in the world. And of all the math majors I know, a lot of them would say this is not easy, right? It's just what it is. Like, this stuff is not supposed to be easy. Yeah. So yeah, again, I guess I don't have to really prove that again, because already the symmetric argument works, because if you swap s and t, then ts equals I implies st equals I as well. A little trick you can play. Suppose V is finite dimensional, and suppose STU are all inside the linear maps, or the operators of V, and then STU composes I. Show that T is invertible and the inverse is U composed with S. Right? Let's see this problem. Right. So in fact, I think right off the bat, you can say T must be surjective, because if it is not, let's say the range, the dimension of the range, STU is bound by the minimum of the dimension of the range of S, and the same for T and U as well, right? But then if T has a dimension less than dimension of V, it's not going to work, right? So that means T is surjective. And if T is surjective, then what you can say is that T is injective, because T is a linear operator. So T is surjective means T is injective, which means T is invertible. When T is invertible, then half the proof is done. And we just gotta show that the inverse is indeed U composed with S. So let's bank off of what the previous problem said. We can use question 10. So if we know that STU is I, and in fact ST composed with U is I really implies that U composed with ST is also I. So ST is really the inverse of U. Then what you can say is, yeah, maybe this is overcomplicated. I don't want to go this way. I probably want to go the other way around, actually. So I want to show S inverse is equal to U. I can multiply things on both sides by S inverse. Right? Tu is equal to S inverse. And then, yeah, okay, maybe I missed something. Shoot. I think one of those things have got to work. Right? Yeah, no, that's definitely not right. Hold on. That's bad. Yeah, no, that's not true. That's not true. Yeah, no, that's not great. Let me think. Yeah, this I think is true. Because I think there was somewhere in the textbook that showed this exact identity. No. Maybe it was an exercise. Oh yeah, no, it was the first. It was the first exercise. Yeah, yeah, yeah. But first you had to show like S T U are all invertible, or at least S and U are invertible. But I think U has got to be injective, because if it's not, then it doesn't, like STU composed cannot be the identity map. That means U is invertible, and then S has got to be surjective for the same reason T is. So S is invertible. So I think indeed you can do this. Yeah, I feel like a lot of the times, like when you're doing linear algebra questions like this, you're just fooling around with notation. You don't really know what the question is asking. You make a series of simplifications until you get to the result, which is always kind of sad to see. It's like you never really understood what the question is about. And I'm here to try and maybe fix that. See a way out of it, perhaps. See some reason behind the questions. Because I sure as heck think whoever came up with these questions knew the reason for why these questions are the way they are. Yeah. Okay, question 12. Are they encroaching on infinite dimensional vector spaces? So I think that's enough for today. I'm not quite happy with that infinite dimensional vector space thing. Let's take a break for today and maybe come back tomorrow.